The trick to living out here is to see just as much beauty when these flowers are not here as you see when they are. When a physicist first kind of approaches SL2C or SL2R or any of those Lie groups, we usually come at it from the point of studying more rotations-oriented Lie groups like SON or SUN, things that act naturally on spaces like R to the n and C to the n. And so we always kind of get put off, at least I did, by Möbius transformations, these fractional linear transformations and so on. And when people try to explain things to us in terms of, well, complex numbers and complex infinity, and you always talk about complex infinity as kind of a point, right? Oh, 1 point. That also kind of breaks our brain a little bit, because when we think about infinity in a kind of multi-dimensional space, thinking again in real dimensions, we are very concerned about where infinity is, because, especially when thinking about like Feynman propagators, for example, you want to make sure that you're closing your contours either above or below, and the direction at which you go about closing those contours, the direction in which you approach infinity, really matters. Now, we probably aren't sophisticated enough in terms of poles at infinity and so on to be able to talk about this sensibly, but hopefully we'll address both of these issues today. Now, SL2C perhaps most naturally acts on C2, right? The two complex dimensional plane, if you like. Something that, as a vector space anyway, is isomorphic to R4. You can act with normal matrix operations on a two complex dimensional vector and get pretty much exactly what you'd expect from studies with the real case. Another kind of source of natural mathematical objects that you can act on with SL2C might be kind of any complex manifold of complex dimension 2. At least locally on their tangent spaces, they should look like C2, so there is some kind of natural action there. So, things like the 4 torus or kind of like a K3 surface or something like that. There's plenty of examples where you might find a good use for SL2C. There are some surprising kind of non-trivial examples where SL2C acts really naturally. A good one is a specific complex manifold of complex dimension 1, the Riemann sphere. And that'll be pretty much the subject of our discussion today. So let's talk about how that might be. As a warm-up, to get started, let's think about the real projective line. Essentially, the real projective line amounts to considering all normal unit vectors in the plane. What are the space of those things? Well, obviously 0 cannot be normalized, but every other real number or member of R2 can be. So what does kind of the unit vector that sweeps through the whole plane sweep out? Right? It's a circle. So yeah, R squared minus point in the origin divided out by the scalars gives us the circle, which is a nice, compact, one-dimensional real manifold, right? Very clean. And as you might have guessed, SL2R kind of has a very natural action on this particular space. Why? Because we're starting with the plane, R2. So we can easily form the complex analog of this thing, the complex projective line by taking C2, subtract out the origin, and divide out by the complex scalars, the non-zero complex numbers. Do you know what we get? Yeah, the Riemann sphere. Mud pile. Don't worry, it's not that muddy. There's no need for this. There's no need for that. Just go through the mud. You're outdoors, give me a break. So needless to say, the complex projective line has a very natural action of SL2C, because we can think of any point in the complex projective line as parametrized by two coordinates, so the two coordinates on C2, subject to all those identifications. These are the so-called homogeneous coordinates, which we can write like this. So pick Z and W to be complex numbers, and we kind of write them with two parentheses like that. You can see that yes, SL2C is going to have a real natural action on this space, just normal matrix multiplication. ABCD acting on the vector ZW gives you what? Some junk there. Yeah, no big deal. But you might ask, well, how are we going to take care of all those identifications, by the non-zero complex numbers? Well, that's a really great question. And as it turns out, you can think of the answer like this. Since any pair of coordinate points in C2, i.e. Z and W, are in the complex projective line, if we allow for identifications, again with some complex number, say lambda, so lambda times Z and lambda times W, we can in particular choose lambda equal to, say, Z inverse, 1 over Z, or W inverse. And so in reality, we have kind of two ways to think about the complex projective plane. We can think about it as parametrized either in kind of Z, 1 or 1, Z. These kind of polar opposites, if you like, can be taken literally to represent two coordinate patches on the atlas that describes kind of the smoothest structure of the Riemann sphere. Right, so it's probably no news to you that you need at least two coordinate patches to describe this two-dimensional manifold, just as a two-sphere, the north and the south, and the missing points, if you like, of the various coordinate patches, north and south, are precisely the poles, the north and south poles. So in one way, you can kind of think of infinity from the perspective of somebody sitting in the northern hemisphere as being the south pole. And in another sense, if you're on the southern hemisphere, you can think of infinity as the North Pole. And because it's such a clean and easy way to think about to think about things, infinity is just a simple point. We can, restrict to pick your favorite hemisphere, northern, southern, whatever. So in other words, we're just going to restrict ourselves to one copy of C, and just simply remember that infinity is restricted to one point. And that point isn't really infinity at all, it's just the antipodal point of the origin. In other words, what I'm trying to say is, in order to make sense out of these really clunky homogeneous coordinates, what we're going to do is we're just going to always demand that the second entry be fixed at unity, Z and 1. And if we run into infinity, we run into infinity. We know where that is. That's at the South Pole. So how does this new perspective affect our study of SL2C? Well, SL2C can act on these now kind of fixed homogeneous coordinates. That is to say, it'll act on Z and 1. And we get, as per usual with matrix multiplication. But remember, so we have A, Z plus B in the first and CZ plus D in the second. We want to make sure that our second entry in our homogeneous coordinates, in our vector that describes the complex projective line, is fixed at unity. So in order to do that, we have to pull out from the vector a quantity CZ plus D, which, lo and behold, gives us this thing out front. And look at the first entry. It's our Möbius transformation, our fractional linear transformation. Cool, right? That's where it comes from. Oh, yikes. I almost forgot to mention. So when we perform that linear transformation and pull out that CZ plus D, that factor there, that's, I guess in the literature, it's called like the automorphy factor. But if you've played around with modular forms at all, or you've been following our discussion on SL2Z or Z for you British folks, you might know that factors of CZ plus D show up all the time. And so one way that we can kind of intuit, or at least roughly, very informally think about these factors is imagine products like tensor products of the complex projective line, right? So imagine you have n of them. So we're talking about the tensor product space t to the n of that manifold. What you can do there is kind of envision you would get n many copies of CZ plus D hanging out. Now, we can sometimes see fractional powers of this thing, and maybe if you want to talk about spin bundles, that makes sense. But either way, it's kind of at least motivation for the fact that it's not crazy to talk about objects that transform under SL2C or SL2Z for that matter, with finite powers of this quantity, this automorphy factor. So hopefully that puts your physics soul at ease, right? That the Möbius transformations are not some kind of weird ad hoc thing, but actually descend naturally when we try to talk about kind of a complex linear transformation in a 2 complex dimensional space on a 1 complex dimensional space. It just so happens that the complex projective line possesses all of that symmetry. It's just realized in kind of a non-linear way, or at least a fractionally linear way. And so indeed, from this perspective, the point at infinity is not a big scary thing. It's just a rotation, in some sense, a linear transformation away from a given point. So if you've got Z on the complex projective line, aka the Riemann sphere, you want to map Z to infinity, great. Pick this matrix here. That's all it takes. But what if you don't want to deal with infinity? Like at all? Unfortunately, for those of you that don't like infinity, SL2C is transitive on the complex projective line on the Riemann sphere, which means that given any point in that sphere, I can take it to infinity just by choosing that matrix we just talked about. So there's really no escaping from it. Well, sort of. There is something you can do. You can consider subgroups of SL2C. Surely there are subgroups of SL2C that won't take you to infinity. So can you think of an example of a subgroup of SL2C that doesn't map things to infinity? Well, let's think about how that might be. So basically you want to avoid the denominator of the map from Z to the Möbius transformation of Z from vanishing. So that means that C, Z plus D shouldn't equal 0, which means that Z shouldn't equal minus D over C. If D and C are, say, real numbers, what do you think we can do? We may have talked about this before in other videos, but SL2R preserves the upper half plane of the complex numbers, which is totally a subset of the complex projective line. And to see this, you need only look at the imaginary part of a Möbius transformation of some point z in the upper half plane. And lo and behold, we find that the imaginary part of z maps to some positive number times the imaginary part of z itself. In other words, the upper half plane is preserved. Moreover, we again see the realization of the fact that it never blows up. The denominator z plus d never goes to 0 because z is always has a non-zero imaginary component, which is very cool, very nice. Ooh, somebody did not have a good time here. Yikes, buddy. Hey, that's life out west. Since we brought up SL2R, it might be fun to describe how linear transformations, things that we would normally think about in a Euclidean space like C2 or out of the 4, kind of get deformed under these fractional linear transformation or these Möbius transformations. So to that end, let's consider a subgroup of SL2R. Specifically, we can consider one that's very familiar to physicists, namely SO2, the rotation group in 2 dimensions. One fun fact about SL2 is the fact that it has a fixed point in the upper half plane. Let's try to see what that fixed point is. So equating some point in the upper half plane, say z, and acting on it by a Möbius transformation of the matrix, say cosine theta, minus sine theta, cosine theta, right? And solving for z, we find, yeah, z squared equals -1. So in other words, I, which is totally in the upper half plane, is the fixed point of the subgroup of SL2R, namely SO2. Now, what does that mean? Well, it means that I is held fixed by rotations, sure, but what else? Well, the actual other rotations, how do other points transform? It's kind of a mess, but there's a really nice, convenient picture that you can draw. So let's go ahead and draw that here. So as you can see, it kind of maps to what you would normally think of as in terms of orbits of SO2. They're definitely closed, but they're squashed in a particular way, meaning that all of the orbits run between kind of the bottom of the upper half plane, the real line, and the point I, and they kind of go all the way around to infinity over at the top. It's not nice and clean, it's deformed somewhat, and that's to be expected. After all, we're not in a normal kind of Euclidean regime. And you may be asking, Sean, what the heck are you talking about? Non-Euclidean regime. C2 is totally Euclidean, right? It looks like a vector space like R4, and everything is intuitive there in terms of rotations and orientation preserving maps, that sort of thing. When we project down to the complex projective line, we've seen that the group of rotations of the upper half plane, right, which should be something that looks like R2, gets squashed. And how does it get squashed? Well, it gets squashed in a very particular way because I guess, if you like, the SL2Z invariant metric on the upper half plane is a non-Euclidean metric. Specifically, it looks kind of like this. You know, the kind of in point coordinates. It's like y squared times dx squared plus dy squared. In other words, it's a hyperbolic space. So if you've ever seen any of the pictures by M.C. Escher, which I won't attempt to steal and show you here, but rather simply do a caricature thereof, you can see that, yeah, SL2R will act naturally on hyperbolic space. Well, hopefully that gave you a nice kind of introduction to how Möbius transformations come about and how the mapping from C2 down to the complex projective line isn't exactly intuitive. So there's a little bit of deformation involved. but also hopefully it motivated for you further study of the upper half plane and all of the interesting subgroups of SL2C that leave that upper half plane fixed. So I guess that's all for today. I'm gonna go head down that way and maybe explore a little bit. Hope y'all are having a great week. Talk to you soon. Oh, I almost forgot. Next time, we're gonna talk about how to map the upper half plane into something that looks a little bit more like those MC Escher drawings, which will also hopefully unsquash a little bit those orbits of SO2 in SL2R. Stay tuned.